The next question that we will solve is question number 8 from exercise 9.3, which is from the chapter of circles. And the problem is that if the non-parallel sides of a trapezium are equal, prove that it is cyclic. Okay, so this is the problem given. So let's try to represent this using our diagram. So a trapezium is a quadrilateral in which two of the sides are parallel. So we have AB and DC as parallel sides. And then we have the non-parallel sides, which is AD and BC. These are the non-parallel sides. It is given that the non-parallel sides of the trapezium are equal. So that means the side AD is equal to the side BC. And since it's a trapezium, we know that the other two sides are parallel to each other. So that means AB is parallel to DC. So we are given that AB is parallel to DC, which is the bottom side and the top side are parallel to each other. And the side on the left and the right are equal to each other. The non-parallel sides are equal to each other. And we have to prove that this trapezium ABCD is a cyclic quadrilateral. Okay, so what is a cyclic quadrilateral? What property must a cyclic quadrilateral satisfy in order for it to be called a cyclic quadrilateral? The condition is that for a cyclic quadrilateral, the sum of the opposite pair of angles is 180 degrees. So we have to prove either that the angle ABC, which is this angle here, plus the angle ADC, which is this angle here. So the opposite pair of angles, ABC plus ADC, is equal to 180 degrees. Or we have to prove that the angle BAD, which is this angle here, plus the angle BCD, which is this angle here, their sum is equal to 180 degrees. So we have to prove that either of the pair of opposite angles have a sum equal to 180 degrees. Okay, so this is what we have to prove. And if we can prove that the sum of the opposite pair of angles in this quadrilateral ABCD is 180 degrees, then we would have proved that this is a cyclic quadrilateral. Okay, so to prove that, we have to make a construction, and the construction is that we draw a line CE, this black line over here, which is parallel to the line AD, such that we have a parallelogram formed given by the vertices A, E, C, D. So we construct a line CE parallel to AD. So CE is parallel to AD to form a parallelogram AECD. Okay, so with this construction now, we can use the properties of the parallelogram and some other properties that we have studied in previous chapters from lines and angles, and go on to prove that a pair of opposite angles has a sum of 180 degrees. Okay, so let's move further. So the first observation we have is that AECD is a parallelogram. We are already given that the side AD is equal to the side BC for this trapezium ABCD, and within this parallelogram AECD here, we know that in a parallelogram the opposite sides are equal and also the opposite angles are equal. So that means since we have in a parallelogram opposite sides are equal, the line CE must be equal to the line DA, or we can say AD and EC are equal, because for a parallelogram opposite sides are equal. So therefore we can say EC is equal to AD, and that's because opposite sides of a parallelogram are equal. Okay, so that's the first observation we have. So we have now EC is the same as AD, but we also know that AD is equal to BC as well. So therefore we now get EC to be equal to BC as well. Okay, so since AD is equal to BC, we now have EC is also equal to BC. Okay, so that's one of the observations we have from this construction now. The next thing we notice is that the parallelogram AECD must also satisfy the property of the parallelogram, which is the opposite angles must be equal. So we have the opposite angle, which is the angle ADC over here, and the angle AEC over here. So these two angles must be equal to each other because AECD is a parallelogram. So we now have angle AEC is equal to angle ADC because opposite angles of the parallelogram are equal. So since AECD is now a parallelogram, the opposite angles are equal. So we have this relationship now. The next thing we notice from the figure is that the angles AEC and the angles BEC are a linear pair of angles. So angle AEC and angle BEC form a linear pair. So wherein we have a line segment AB on which the ray EC is standing. So angle AEC and angle BEC are a linear pair. So BEC is this angle over here. So that's these two angles form a linear pair. And since angle AEC and angle BEC are a linear pair, we know from the property of the linear pair of angles that the sum of a linear pair of angles is 180 degrees. So we have angle AEC plus the angle BEC to be equal to 180 degrees. Okay, that's the next observation that we have. Now then what we do is we look at the triangle CEB. So this triangle on the right here, when we look at this triangle, we have the side EC is equal to the side BC. So this is an isosceles triangle. And in an isosceles triangle, we know that the angles opposite to the equal sides are equal. So therefore, angle BEC must be equal to the angle EBC as well. So this angle must be equal to this angle because these two angles are opposite to the equal sides. So let's write that down. And once we have that, we will have enough information to prove that the sum of the opposite angles in this trapezium is 180 degrees. And thereby we could prove that this is a cyclic quadrilateral. So we now have in triangle CEB, which is this triangle over here, we have the angle BEC to be equal to the angle EBC, which is this angle here. So these two angles in red are equal to each other because these are angles opposite to the equal sides of this triangle. So this is an isosceles triangle where two sides are equal. And we know from the property of isosceles triangle that the angles opposite to the equal sides are also equal. So therefore angle BEC is equal to angle EBC, which is what we have here because these are angles opposite to the equal sides. So now we have the information we need. We have angle from this expression over here, we have angle AEC plus angle BEC to be 180 degrees. So if we can write a number to this equation, so let me write a number. So I'll call this as equation 1. So in our expression, we have angle AEC plus BEC is 180 degrees, but the angle AEC over here is the same as the angle ADC because we have shown earlier that these are angles, opposite angles in the parallelogram, and opposite angles in the parallelogram are equal. So we have when we substitute in place of AEC in equation 1 that AEC is equal to ADC. So we will have so let's write equation 1, angle AEC plus angle BEC equals 180 degrees. But we know that angle AEC is the same as angle ADC. So in place of AEC, we write angle ADC plus angle BEC is the same as angle EBC, which is this angle here. So in place of BEC, I'm going to write EBC. So that is angle EBC. So that is equal to 180 degrees. So we have basically substituted in equation 1 the opposite angles which were equal that we have obtained earlier. So we have in place of AEC, we have substituted ADC because AEC is equal to ADC. We have shown it earlier. And similarly, in place of angle BEC, we have substituted angle EBC. So now we have angle ADC plus angle EBC as 180 degrees. So angle ADC is nothing but this angle over here, which we have marked already in black. And the angle EBC is this angle over here. So we have now shown that in this quadrilateral ABCD, we have a sum of opposite pair of angles to be 180 degrees. And since the sum of the opposite pair of angles is 180 degrees, we can now state that ABCD is cyclic, because for a quadrilateral to be cyclic, the property that has to be satisfied is that the sum of the opposite pair of angles is 180 degrees, and we have already shown that the sum of the opposite pair of angles, that is angle ADC and the angle EBC, which is this angle, so these are the opposite pair of angles of this quadrilateral ABCD, and this sum is equal to 180 degrees, and therefore we will have ABCD as a cyclic quadrilateral. So therefore we state that ABCD is cyclic. Okay, so we had to prove that the trapezium ABCD is a cyclic quadrilateral, and the only information we were given was that the non-parallel sides are equal. Okay, so we made a construction by joining CE such that CE is parallel to AD, so that gave us a parallelogram AECD, and then we used the properties of the parallelogram to find that the opposite angles are equal, and then we also applied the property of the linear pair of angles to get this sum as 180 degrees, and from that using the isosceles triangle property for this, we obtained that the angle BEC is equal to EBC, and then we substitute that back in the linear pair sum to get the sum of the opposite pair of angles to be 180 degrees, which we have proved here, and that gives us the conclusion that ABCD is a cyclic quadrilateral. So the trapezium ABCD is a cyclic quadrilateral, or we say simply the ABCD is cyclic.